So in the Schoology, there is a set of notes called Bonding Orbitals and Molecular Orbital Theory. As always, you may use those notes or take your own and then submit summary and questions when you're done. All right. So when we think about covalent bonding, we think of that forming through the sharing of electrons by adjacent atoms. So here's a hydrogen atom, here's a hydrogen atom. They share electrons through a direct overlap, and we get a bond there, right? We can also take, here's a hydrogen, and here's a chlorine molecule, and that chlorine has a single electron in a 3p orbital, and so they'll overlap, and we get a bond there. Right? Same thing here. Chlorine has a single electron in a 3p orbital. Another one does as well, and so those p's overlap head to head, and you get a bond there. Okay, so in such an approach, this can only occur when orbitals of the two atoms overlap. Okay, this is easy to see in binary situations where we just have two atoms coming together. But what happens if things get more complicated? Well, you get something like when you get a cross between a horse and an eagle. A horgle, an eargris, a hippogriff, regardless, it's a hybrid. It's a mix of the two. Okay, really, that's fictitious, but nonetheless. All right, so sometimes in bonding, we end up with hybrid orbitals. Hybrid orbitals occur when we take orbitals from one sublevel and mix them with another. Okay, if we think about beryllium, here's beryllium's electron configuration. And in its ground state, beryllium would not be able to form bonds because there's no electron to share. They're already paired up. But if we boost the amount of energy in beryllium just a little tiny bit, we can take an electron from the 2s up to the 2p. In that particular case, then, we end up with two orbitals that have one electron each in them. However, that can't really happen either. So what does happen is we actually mix those two orbitals, and what you end up with is two equivalent energy orbitals that are hybrids of the two. We call them sp hybrid orbitals. Why? Because they're made of an s and they're made of a p that are mixed together. And when that happens, our probability of our electron cloud changes from having shapes that look like this to ending up with two hybrid orbital shapes that look like that. Those are our sp hybrid orbitals. Okay. In the sp hybrid orbitals, one of the lobes is larger and more rounded, as is the s orbital as well. Okay. Sort of like that. So we actually take these two and we, of course, sort of overlap them, and all together it kind of looks like this. So like an s or like a p orbital, but sort of with some bigger ends on it. Okay. So only showing those large lobes. We also have the other area of probability, which is inside here, but that's not going to make contact with other atoms. So it's this larger orbital that we're worried about in terms of where the electrons can come into contact or invade the space of another atom. All right, so then those two hybrid orbitals that we just created would align themselves at 180 degrees from each other. All right, so here's our beryllium in the middle. Here's the one hybrid orbital. Here's the other hybrid orbital. Okay, and they align themselves at 180 degrees from each other. Okay, the electrons are going to get as far away from each other as they can. This is consistent with the observed geometry of what we see in beryllium compounds. They typically bond linearly. Okay, so if I have a F, again, fluorine has a single orbital that has a single electron in it, so it's just a straight up 2p orbital. It comes in and it's going to overlap, so we get one electron from the sp, one electron from this p, we get an overlap there, and voila, we get a single bond. Okay, same thing happens over here with our fluorine on the other side, and we get a single bond there as well. Okay, so by hybridizing the orbital and making an sp orbital, beryllium now has the ability to make two bonds 180 degrees from each other, giving us linear geometry. If we wanted to write an electron configuration for this, what would it look like? Well, the sp orbitals are higher in energy than the 1s, but they're lower than the 2p. So we would just create our sp orbital right there in the middle. You will never ever be asked to write an electron configuration. We just want you to think about what that hybrid orbital would look like in an electron configuration orbital diagram. Okay. If we do the same kind of thing for boron, where the electron configuration looks like this, we go, okay, well, if we hybridize these together, we can come up with a thing that looks like this, an electron configuration that looks like this, 1s, and then we would go sp2, where we now have 3 orbitals that have 1 electron each in them. We do that by simply moving one of these orbitals over to here. What does that leave me with? Well, it does leave me with a single unoccupied 2p orbital, just like I had before. So that's what I would do that. Okay, so now we've taken this s orbital and 2 of these p orbitals, and we've hybridized them together. An s orbital and 2 of the p orbitals, and we hybridize them together. And now we get a set of 3 orbitals, which again, by Vesper theory, are going to move away from each other as much as possible. And so when they overlap, we get this shape right here. Okay, so sp3 hybrid orbitals together, and we show just those large lobes where they're going to be able to overlap with other things. This means that for boron, we're likely to get 3 possible bonding spots, which is consistent with what we see in boron molecules. We end up with boron geometry that is trigonal planar and have a bond angle between them of 120 degrees. Right? With carbon, then, going up one more, right? So carbon is 1s2, 2s2, 2p2. So now if we give one of these electrons in the 2s just a little bit of energy, we can pop it up to that orbital there and then hybridize these together, giving us an electron orbital diagram that looks something like this. Which is made of an s and 3p orbitals. And so we end up with 4 orbitals that all have the same energy that are sp3. Okay? If we do that, we then again end up with 4 hybrid orbitals. If we make them overlap, they're going to end up 109.5 degrees apart from one another. Okay? That, once again, is sp3 and gives us a tetrahedral geometry. Okay? Now, hybridization is a can, it's not a must. So we don't have to use all of those orbitals in that way. We could keep some as p's, etc., and not do it and not hybridize if that gives us an electrical or an energy advantage. Right? And in the case of carbon, that happens sometimes. Sometimes carbon only needs to hybridize to sp. Sometimes it hybridizes to sp2, and sometimes it hybridizes to sp3. Depending upon how many bonds with direct overlap on the ends we need to make to fulfill an octet rule. Right? So what does it look like when atoms use hybrid orbitals to bond? Okay? Because hybridization is a major player in this in an approach to bonding, the valence bond theory, and there are 2 ways that orbitals can overlap to form bonds between atoms. One of them we've already talked about, and those are sigma bonds. Okay. Sigma bonds are when we have head-to-head overlap, just like that. So a p orbital overlapping with a p orbital, or a head of an sp orbital overlapping with the head of an s orbital. It's head-to-head, and it basically ends up with a bond that's formed in a linear manner straight down the nuclear axis between the 2 atoms that are involved. Those are sigma bonds, head-to-head overlap. Okay. But as I said, sometimes we have some leftover p orbitals that aren't being used, that don't get hybridized. And if you think about p orbitals as being propellers, you can imagine that here's atom A, here's atom B, and you can imagine that they both have propellers that stick up and down. that might have a single electron still sitting in them, okay? Well, if that's the case, we actually set up a situation where if these atoms get close enough to one another, these electron clouds will actually overlap one another from side to side. Now, the propellers do go up and down, and that's one orbital, so they can overlap on the top and overlap on the bottom. That side-to-side overlap of our p orbitals is called a pi bond. Okay, so side-to-side overlap, so here's a p orbital, and here's a p orbital, and they overlap, and we've created a bond. Okay, so this is just one bond. Okay, the electron density exists above and below the internuclear axis, and this is usually made from unfilled p orbitals that are adjacent to atoms that already have a sigma bond. So if they already have a sigma bond and we're adding a pi bond, that's how we get multiple bonds. That's how we get double bonds and triple bonds. Okay? So single bonds are always sigma bonds, okay, because overlap with a sigma bond head to head is greater, and so that's going to create a stronger bond and lower energy. Okay, they're just coming in straight head to head. That's a nice strong overlap right there, and so it tends to be a stronger bond with more greater energy lowering happening as a result. Multiple bonds, double bonds, and triple bonds, one of the bonds at least is one bond is a sigma bond, and the rest of them are pi bonds. So in a single bond, we just have a sigma. In a double bond, we have one sigma, and the other one is a pi bond. In a triple bond, we have one sigma, and the other two are pi bonds. Okay, we represent single and triple bonds nicely using these lines, but if we looked at them in actual 3-dimension using electron cloud probabilities, they would look a little bit different. Okay, so here's an example of a double bond. Okay, in a double bond, we have a carbon that undergoes sp2 hybridization. So that means that we have an s and two p orbitals that come together and make this trigonal planar shape. That means we have a p orbital that's left over that goes up and down. Okay. On the other end, we have an oxygen. The oxygen has also sp3 or sp2 hybridized. So here's our sp2 hybridization. In this one, we have two leftover unshared pairs of electrons on that end, but we still have a p orbital up and down that's not being used. Okay, so in the process, we end up with one electron from here and one electron from there that gets shared in our sigma bond. We have the two lone pairs over there and the two lone pairs over there. We have an electron from here and an electron from the hydrogen. Those go to overlap. There's another sigma bond. And here's another sigma bond over on this side where this hydrogen and one of the lobes of that sp hybrid orbital overlap. Okay, that leaves us with the p's up and down. Okay, that's going to give us an electron here and an electron there. Those p's up and down, they do the side-to-side overlap, forming another bond. So there is our pi bond. And again, this whole thing is the pi bond. So we end up with a sigma and a pi, and so we end up with a double bond. Okay, looking like that. Okay. Again, those unhybridized p orbitals overlap in a pi fashion. In our folder, there is a video of this happening. It's in a screen that looks like this. We'll call it Video Double Bonds. Take a moment, go watch it. It's 1 minute long, and then come on back to this video. Hopefully you can see now a little bit better about how a double bond forms. Okay. Triple bonds happen when you have two sp or hybridizations happening. Okay, so in this particular case, we take our carbons, and in this particular case, they've only sp hybridized. So here's one sp hybrid orbital on a carbon, and there's the other. Here's an sp hybrid orbital on the carbon, and there's another one, and we get a nice sigma overlap between them. That means that we've got two pair of p orbitals that are left over, and those go up and down, so we're going to go to side-to-side overlap there. But we also have another set of p orbitals left over that are front and back, and so we're going to get an overlap there. Okay, so you get one sigma bond a pi bond here, and a front and back pi bond there, giving us a triple bond. And so this looks like that. Okay. So again, single bonds, just sigma overlap. Double bonds, a sigma with a pi, and a triple bond, a sigma with two pi's. Here's another video of this happening. I've posted this in the folder, and you can go ahead and take a look at that, and then come on back when it's done. This one's a bit longer. All right. So this valence bonding theory helps us understand or recognize how resonance works as well. Right? So if we drew the nitrate ion, we would see resonance structures just like that. Hybridization helps explain this resonance. Okay, how do we get a double bond here and then a double bond there and a double bond there? Well, in reality, what we have going on here is we have the 4 atoms in the nitrate atom, each has an unhybridized p orbital. So after their hybridization happens and we get some sigma overlap, what we have left is a nitrogen with an unhybridized p orbital, and each of the oxygens have one. Okay. That makes for an opportunity for us to get some side-to-side overlap. Well, it also makes an opportunity to get some side-to-side overlap here and there as well. So now you have an electron with an area of probability that it can move through that is actually all of this, including all of that down under there. That is our resonance structure. So we don't just have a double bond happening here, we actually have sigma bonds down here and sort of one giant pi bond structure on the top and the bottom that the electron can move around in. Okay, it's be delocalized. It's not with a single atom along the way. And so as a result of that, you get resonance. So again, this means that the pi electrons are not localized between the nitrogen and one of the oxygens. They can move throughout any of the pi structure. This also happens in an organic molecule that we called benzene. Way back when we were learning how to about organic compounds, we did talk about benzene a little bit. And what benzene basically has is it has a sigma bond of overlap between all of the carbons in a 6-carbon ring. And then there's a leftover set of p orbitals in that 2p sublevel all the way around the ring. So again, we can get side-to-side overlap around this other thing. So when we conceptualize this, we usually think of it as being an overlapping or an alternating structure of single and double bonds. But in reality, these are all just a blend of these, a sigma in each area down around the ring, and then one giant pi structure all the way around the top and bottom that the electrons can move around in. Okay, and so that's delocalized. And so as a result, that double bond can really be conceptualized as being anywhere around the ring. It's a hybrid, so it's not really a double bond. It's like 1.5 bonds all the way around. All right, so here's our hybrid orbital summary, and when we start to ask about things, it's helpful to refer back to this. Okay, so if I have just a couple of s orbitals bonding, we're almost always going to have a single bond. This happens when I only have one electronic domain. Okay. If I have sp hybridization, I can tell I have sp because there are 2 electronic domains. Like when we're counting out Vesper, trying to figure out Vesper. What's possible for there? We can get a single bond. If I get sp2 hybridization, that gives me 3 electronic domains, like in trigonal planar, but the kinds of bonds that are possible are still all just single bonds heading overlap. Okay. In sp3 hybridization, I can get 4 single bonds forming with head-to-head over all of the top of them. Okay. Now, again, in the case of carbon, we can have partial hybridization, sp2 with a p left over. That gives me 3 electronic domains. which tells me that I'm going to have some single bonds, but somewhere in there I'm going to have a double bond or a resonance structure. If we have an sp with two p's left over, that's going to give me a sigma bond, a pi bond, and a pi bond. Okay, that will give me an opportunity to produce maybe some singles on the ends, possibly a double, possibly a triple, or a resonant structure. And again, two electronic domains there as well. Okay, so that's kind of how this works out. Biggest deal is almost every single double bond is formed from an sp2 hybridization, and every single triple bond is formed from an sp hybridization. All right, so that's valence bond theory. One other theory of bonding that comes out is something called molecular orbital theory. You don't need to know what this is, but you need to know that it exists. Okay, because valence bond theory effectively conveys most observed property of molecules, but not all. Okay, and we're not even going to talk about what those are. Okay, but what you do maybe need to know is that molecular orbital theory exists, and what it does is it considers the wave nature of electrons and consider an orbital as belonging to the whole molecule, not individual atoms. Okay, it's needed to explain how molecules absorb light, giving them color. So again, for molecular orbital theory, the only thing you need to understand is that it involves, or it brings in, the wave nature of electrons to help us understand some aspects of bonding just a little bit better.